Okay, welcome back. It's Vectors Part 2. All right, how are we going to be using vectors for our work in physics? Well, there's two things that we need to be able to do. We need to be able to put vectors together, and you've already done that by practicing addition. You learned that if you have a vector that is pointing this way, and you have another one that's pointing that way, you can add them together to get a vector that's pointing that way. But we also need to know how to take them apart. So, supposing we have a projectile, something that's launched through the air with an initial speed of 20 meters per second, and let's say it's launched at some angle relative to the x-axis, relative to the horizontal, maybe let's say 35 degrees. We know from common experience that that projectile will follow a path, a very familiar path, which is mathematically a parabola, a parabolic shape. And we know that as it flies through the air, that it's going to pass through the x dimension as it moves left to right, but it's also going to be moving through the y dimension as it goes up and down. It's going to be moving through both of those dimensions at the same time, and we need to think about each of those dimensions separately because the y dimension, as we know, involves gravity, but the x dimension has no gravity at all, has no acceleration at all. So when we're thinking about the y dimension, we will expect our projectile to be obeying y equations that involve the acceleration of gravity as it goes up and as it goes down. But while it's traveling through the x world, we expect that since there's no acceleration in the x world, that the object will have to obey equations that have no acceleration. And so therefore we need to take this velocity vector, which is a mix of the x and y world, and we need to purify it into its x and y parts. We call those parts components. This vector is the x component of the velocity, and this one is the y component of the velocity. You'll notice that the x plus the y, according to how we add, is equal to 20, the total velocity. In other words, the velocity in the x direction, vx, plus the velocity in the y direction, vy, equals the total velocity v in vector language. The vy will be the initial velocity, the velocity at the starting initial moment in the y direction. There it is in that equation, there it is in that equation, there it is in that equation. And the Vx will be that velocity in that equation. So before we can think about how an object moves in the y dimension, we have to take the mixed velocity and purify it into y, and similarly take the mixed velocity and purify it into x, and then we think about each dimension separately. So now let's examine how we take the total velocity and break it into its two parts. We know if we break it into Vx and Vy, then the angle right here must be a right angle, and so all of the rules from trigonometry for right triangles are valid. So remembering the standard definitions for sine, cosine, and tangent, we can see that the sine of 35 degrees must equal the opposite over the hypotenuse, and our opposite is Vy, our hypotenuse is V. So we can solve for Vy here by multiplying both sides by V, giving us V sine 35, multiplying both sides by the V, and our V is 20. 20 sine 35, put it into your calculator and you get 11.45 meters per second. So that means the starting velocity in the y direction is 11.45 meters per second. That's how much of the 20 is pointed upward. How much of the 20 is pointed to the right? Well, we can use the definition of cosine. Cosine of the angle, by definition, is adjacent over hypotenuse. Our adjacent is Vx, our velocity in the x direction, and the hypotenuse is the full velocity v. Solving for Vx, multiplying both sides by v, we have Vx, when it gets all by itself, is equal to v times cos 35. That's 20 cos 35, and that works out to 16.38 meters per second. So the x part of the velocity is 16.38 meters per second. So that's how you take a velocity and break it up into its x and y parts. And you can always use SOH, COT, sine, cosine, and tangent because you made sure it was a nice right angle by breaking it up into x and y. Alright, let's try putting one back together. Supposing in some other problem we are following the path of some projectile flying through the air, and we just so happen to know that the x velocity at that moment is 12 meters per second, and the y velocity is 5 meters per second. Still on its way up. Supposing we want to know exactly how much total velocity it has at that spot, well, then we can add those two together like we know how. So we should be able to take our vector that is 12 units long. Uh-oh, where did it go? Hold on. Stand by. We should be able to take the vector that's 12 units long and the vector that is 5 units long, and we should be able to add those two together according to the rules of vector addition. And sorry about the redness of that one there, but the total would be that, and so we would just have to Pythagoras those two to figure out how big the hypotenuse is. So to Pythagoras, our hypotenuse is the total v. That's what we're after. So c squared, in this case v squared, equals a squared plus b squared. So a squared is vx squared, and b squared is vy squared. I think I said that right. And so we have 12 squared plus 5 squared equals v squared, and that's 144 plus 25, that's 169 is v squared. Take away this, take a square root of both sides. Having problems with my pen. And we find that v equals 13 meters per second. That, however, is not a complete description of our vector v up here, because we have failed to mention exactly what angle it is making relative to the x-axis. So what is that angle right there? We need to figure that out. So to figure out that angle right in there, we can use maybe tangent, because we know that by definition tangent of that angle should equal opposite over adjacent, and our opposite side is clearly 5 meters per second, and our adjacent side is 12. So we're looking for the angle whose tangent is equal to 5/12. To get the tangent of the angle, well, I should say to get the angle outside of the tangent function, because right now it's buried inside this tangent function. To strip away the tangent function, we can use a feature on your calculator called inverse tangent. You're probably familiar with that. So if we inverse tangent the left side of the equation, that will undo the tangent, leaving behind only the angle itself. But if we inverse tangent the left side of the equation, we must also do that to the right side of the equation. And so we type that into our calculator and discover that the angle in question is 22.61 degrees. So a complete description of our velocity at this spot in the projectile would be, it is a velocity of 13 meters per second traveling at an angle, current angle of 22.61 degrees. Notice that that angle is indeed relative to the x-axis. That's the standard way that you measure angles. So, to summarize, if you have a known vector A and you want to know its components, ax and ay, ax, as shown to the right, should equal the full vector A times the cosine of the angle theta, which is the angle between the x-axis and the vector itself, and ay can be figured out by the full vector A times the sine of that same angle. If you want to instead know about the full vector A, and you know its components ax and ay, you can figure out the full vector A by taking the Pythagoras of ax and ay. That would be ay squared plus ax squared square rooted. And if you want to know the angle theta that it's pointing in, then you could take the inverse tangent of the opposite side. I got my ax and my ay switched around. 1 second, please. Sorry, there, that's better. We could take the inverse tangent of the opposite over the adjacent. That is ay, the opposite side, over ax, the adjacent side. So to summarize, if you know a vector's magnitude and direction, you can figure out the x and y components. So to go from a vector to its components, you can break it up as shown above. And on the other hand, if you know the components and you want to know the full vector, you can Pythagoras the x and y to figure out the magnitude, and you can inverse tangent the y and x components to figure out the proper angle to describe its direction. Good luck with the problems you have. You can refer to this video anytime you like to freshen up. Good luck, folks. See you Monday.